I just like the hard copy. The hard copies work.
Videos that I post now are like 10 minutes long.
But we're in class. We're in class.
Now it is.
We do all. Yeah, yeah.
Glad we got that up. So, all right, ladies and gentlemen, full disclosure. We are currently recording, all right? Audio, no video, but still. Okay? All right. As promised, the first part of class today, I wanted to go through what we've done over the past week and a half, based on two-dimensional collisions, conservation of momentum in two dimensions. I am going to turn on some lights because some people might want to write some things down. Yeah, you can see because you're right up.
Let's think about.
How's
Lights on, raise your
all right. So.
lights off.
If this was democracy, we'd be in luck, but bureaucracy. It's always my response to that question. So, all right.
That makes me a little.
So, come on.
Yeah.
I mean, I've only watched it once, but it's so definitely burned in my mind. All right. So, it's one of those movies that like USA picks up for a weekend and plays like 10 times in a row. You know, so. All right. First problem that we talked about was called an inelastic collision. An inelastic collision consists of two objects that will run into each other and then they bounce off of each other. Something that we have to keep in mind. In any kind of collision that we have, momentum is conserved. That means that the way we defined it before, sigma pi equals sigma pf, still is true. But when we deal with the two-dimensional aspect of a collision, we have to expand that definition a little bit, right? So we said that in two dimensions, the idea that momentum is conserved still is true, but now we have to look at each axis individually. So momentum is going to be conserved on the x-axis, sigma pi on the x equals sigma pf on the x, right? And then momentum also conserved on the y-axis. That the total initial momentum on the y-axis has to equal the total final momentum on the y-axis. Good there? All right. So let's talk, and let's grab these things. Oh, not really what I wanted to do. Go here, and then go. Okay. So there's our two objects. First thing we said, like we talked about, this is going to be an inelastic collision. The problems that we did in class consisted of this object moving in this dimension, or in this direction to begin with, and then it collides with the blue object, right? And then after the collision, the blue object goes off like in this direction, right? And then the red object goes off in that direction, right? That's kind of problem. That's the first example problem that we did in class. Right? So we talked about the idea that this is sort of the breaking point. This is the dividing line, and that this would be our initial condition, and then this would be our final condition. One thing that we had to keep in mind throughout the whole unit is that it's momentum that is conserved, right? So before we start the problem, we need to calculate the momentum of the objects beforehand. In this case, there was only one object moving, right? The red one was moving towards the right. Blue one was stationary, so it didn't have any momentum to begin with. Then, once again, we still have to calculate momentums. Okay? But now we make use of the two-dimensional idea the component idea, and we talked about that this has an x component and a y component, and that this one also has an x component and a y component. If the red object was originally moving along the x-axis, what should we see about this one and this one? They should be equal but opposite in direction. One points up and one points down. Not that they're both 0. I didn't mean to do that, but that's not what that means. But here on the y-axis, these two components will have to cancel each other out because the original momentum was all along the x-axis, right? I guess we should call those like y and y. We can call it negative y if you want. All right, we good there? Now, on the x-axis, in order for momentum to be conserved, if this is red x and this is blue x, right? These two components together need to add up to this original component. Good there? These two x components together need to add up to this because this was the original momentum on the x-axis. For momentum to be conserved on the x-axis, whatever we started with, we better finish with. Are we good there? That was the first kind of problem that we did. Places where you can find practice problems of this nature. First, Tuesday, February 28th, was where we introduced this problem, inelastic collision. So we talked about collision in 2 dimensions, blah, blah, blah. In class, the problem set that I gave you guys on the very first day of the unit says collisions in 2 dimensions. We did problem set number 4 and problem set number 5. Right? That problem set looks like this. Okay? There's cars on the front, there's a duck up there, duck and a goose. Okay? Problem set number 4 and number 5 are problems similar to this. Okay? Also, for homework, problem set number 6, very, very similar to this as well. Okay? I recorded some things in class that we did when we introduced the example problem. Also, the answers to that problem set are posted online as well. Good there? The next kind of problem that we did was also an inelastic collision problem. Changed mine apparently. Where had a red object, right? Okay, okay. You can do that anyway. Call that blue. And then red object. Okay. Once again, the red object moving to begin with, not straight. The red object moving to begin with, then red goes off in this direction, blue goes off in this direction, but they didn't tell us either of the final velocities. Okay? But the one thing that they did tell us was if we measured this angle red theta and this angle blue theta, it turned out to be a 90-degree angle. Okay? Hopefully, does this sound familiar? We did this problem in winter. Well, if we go here, and I'll adjust these. No, that's actually pretty easy. If we move that blue one like this, we end up with this being a right angle. And then, oh, this one. This would actually be the final momentum. But it just so happens to be the hypotenuse of a right triangle. even though I didn't draw it right there. Here, move that to it, not like that, like that. Because it's horizontal, right? Whatever initial momentum that the red ball had before the collision has to go here. Okay? Then you'll have a right triangle where you know the hypotenuse, it's the purple line. You'll know one angle, you should know the other angle, and you should then be able to figure out what this component here is and what this component here is. That just so happens to be the final momentum of the red and the final momentum of the blue. Does that sound somewhat familiar? Where can I find problems like this? Wednesday, February 29th. This problem in class from the book, page 216, number 18, was a problem similar to that. This problem from the book, similar to that. This problem from the back of the book, similar to that. Okay, so we got a couple of options there. The problem set, number 7 and 8, those are more similar to the original kind of problem that we did, where you had one of the final velocities and you can figure out the momentum there, break it into components, blah, blah, blah. Also, class recording there. So you have an option taking a look at it again, seeing how we did it, stuff like that. Okay. Good there? Other things to look at. Hover Puck Collision Lab. It is graded. It's over on the bottom over there. So if you want to take a look at that, all of us did pretty well on it. A couple of things here and there, but most people did pretty well. So if you want to take a look at that when we're done, might be a good idea. A couple of minor things there and there. All right, good there? The last kind of problem that we did, we had, oh, that's a little too big. We had blue objects, lucky this is on recording. You can just fast forward this part when you watch it, if you watch it. Yeah. I just, it's there for you. All right, red object moving in this direction. Blue object moving in this direction, right? They come together. Whoa, that's a little too big. Okay. They come together. Nope. Well, because we said in this kind of problem, they stick together, right? So two objects come together and make one object, right? Everyone get it? So in this case, these two objects come together, they stick together and move off together as one object. We referred to this kind of collision as a perfectly inelastic collision. Say again? Nope. Perfectly inelastic collision. The fact that it's perfectly inelastic means that they stick together and become one object. Okay? But once again, momentum is still conserved on the x, still conserved on the y. So this has some momentum that goes off in this direction. Okay? As we've done before, this object has components, right? Looks like this. Looks like this. Okay? If the blue dotted line is the y component of the final momentum, where this is equal to momentum, right? Technically, it's the final momentum. If this blue dotted line represents the y component of that final momentum, it had to come from here, because this blue solid line was the only momentum on the y-axis before they ran into each other. Right? And then same thing here. This x component had to come from this momentum here, because it was the only momentum on the x-axis before the collision. This is similar to what you did in the crash scene yesterday, Tuesday, okay? When the two cars ran into each other, they stick together. Okay? Now, with this information, we can figure it. We have the two sides of this triangle, right? We have this component here. You have this component here. With those two components, you should be able to find the final momentum, right? Also, as well, you're going to need some kind of angle there because you need a direction, especially if you're doing velocity. And you can figure out all those things because on this right triangle, you have two of the sides. Get there? Problems like this. Monday, March 5th. Class recording of in-class example problem. We did a couple of problems from the book. The problem set that I gave you, question number 1 and number 2, very similar to the two example problems that we did in class. Also, the crash scene analysis that you did over the past couple of days had an aspect of this where the two cars ran into each other. And those are the kind of problems that we did. Questions? Question?
Yeah, that's a good question.
Okay. Any questions about the test? Like I said, example problems we did in class, answers to the problem set that we did, they're all posted online, so you can check those out. The problem is, or the test is going to be very problem heavy, right? It's almost all, say again?
How many problems?
Well, we went over 3 types of examples, so the most we could probably have on there is going to be 3 problems. Okay.
I thought we were.
So. Say again? Yeah, no card, go ahead. Yeah, that's fine. So. Okay, do you know card if you would like? Like I said, now you can have example problems on the note card, that's fine. So that's pretty much all you would have here. So.
How many? I mean, there's like you said there were.
There's multiple choice.
A couple multiple choice, say about 3, 4, 5 maybe. So, but a large majority of your score on the test will be determined by problems. All right, I will post this online sometime today, so you can check it out tonight if you want to read, look at it again. Also, I'll post the slides up, so if you want to check those out, you can as well.
Wait, that's it?